thank you everyone for joining us today. We are here to talk to you guys about how we, as consultants, grow machine learning platforms in enterprises and federal specifically. A little bit about us. I'm Hussain Sultan. I've been doing data science and leading data functions at numerous enterprises before. Today, I'm at MetroStar building out the AI practice. Joining me here is Ben Lindquist. Ben, would you like to introduce yourself?
Certainly, Hussain. Hi, I'm Ben Lindquist. I have a lot of experience in highly scaled backend systems, particularly in ad tech. I was the CTO of Ad Juggler, where I built a transaction processing system for ads that could do millions of transactions per second. I've taken that scaling experience and applied it to machine learning and AI for the past 4 or 5 years. I've been working on algorithmic trading, evolutionary hyperparameter tuning, and some other fun things like that. Happy to be here and talk to y'all today.
How about Nathan?
Hey guys, I'm Nathan Barber. I have experience in cloud computing with Node.js and Python, but recently I've been applying more attention to MLOps and DevOps within this field. So nice to be here.
Well, thank you so much, Nathan and Ben. So a little bit about MetroStar. MetroStar system is about 21 years old. We are spread across 3 practice areas, and we are investing over $2 million a year in AI R&D. So just speaking about machine learning platforms, what is a machine learning platform? So some foundational components that we have observed in our consulting practice is that you start off with a developer experience. So what that means that, do you have efficient tools to do interactive computing? Do you have notebooks? Do you have IDEs? Do you have a great experience for the developers? And then on top of the experience, do you have all the tools and frameworks and libraries that a developer or a data scientist might need to do machine learning experimentation or other analytics tasks? You also get into compute and data. And in this case, compute could be on-prem or on cloud. It could be Raspberry Pis. And you need to understand how the enterprise will be able to deploy and to consume those compute resources. Data is a challenge, and a very important capability that we need is from an access perspective. Can you securely access your data? And then how is your data being stored and upkept? In enterprise, you generally have large teams or many teams of data scientists. How do you collaborate across those teams? And in this case, collaboration could be sharing of notebooks, but it could also be experiment sharing and showing results to your stakeholders. Serving and monitoring is a very important part. How do you take your machine learning experiments and your machine learning models to production and to your end consumer? And monitoring is are you predicting within the bounds that a machine learning model was built in? So tracking that sort of growth trajectory or maturity trajectory, we observe about four phases. Gartner does 5, but we've simplified a little bit. So the foundational bucket, we basically think that a lot of folks have analytics or data science needs that are medium to small data or bound to medium to small data. That means that your data can comfortably fit into your laptop or workstation or a server. The second bucket in this growth or maturity model is the experimentation stage. And in this stage, you are experimenting with perhaps larger than memory data. You may require some scale, and you are trying to come up with the justifications for AI or machine learning use cases. The third bucket is the institutional, and that's where you might be looking into multi-tenancy. You might be just scaling your like machine learning platforms across multiple types of users or user roles. You will also be looking at optimizing your costs and the small data science team workflows. So maybe investing in like standardized machine learning pipelines. Mapping that onto our PyData stack, it turns out that you can actually grow and traverse this trajectory very well by just leveraging and just scaling the PyData core tool stack. So you start off with the de facto data science platform. These things are pandas data frames. These are your Jupyter notebooks. These are your scikit-learn. And as you're experimenting with like larger or out of core data, you might be looking at Dask. As you have multiple data scientists, you might be looking at multi-tenancy with Jupyter Hub. You might have some of the best practices at this point with like conda packaging. Growing further on this, you will then be able to, perhaps integrate with your data management platforms like Hadoop through Skein. You have like Dask Gateway that is like multi-tenancy for Dask clusters. You may be optimizing on CUDA and GPU workflows. And on the scaled bucket, the example, which is a great one, is Pangeo. Pangeo is the machine learning platform for earth sciences, and it has been sort of to grow. It grew in a just similar trajectory and has just similar tool sets. In our journey, some of the common challenges that we might have, the first one, and that's the key, is how do you procure the open source packages within the walls of an enterprise. And like that could be that, hey, you want to upstream to mirror your open source or your community driven artifact repositories, so to Conda Forge, to channel on Anaconda. You might also have some licensing and governance part to it as well, that you may want to whitelist certain types of licenses. The second challenge is the enterprise integration and data. This is where you are integrating with the current or existing technologies that your enterprise might have already adopted. This could be as simple as just security or auth integration, but it could be more advanced around building new services for tracking machine learning experiments, or creating drivers for data access and quality and quality reporting. The third challenge is the new scale, right? So like, as you know, machine learning is a data hungry process, and it will consume all the data, and you might need to build more complex models using distributed training techniques. You might have hyperparameter tuning that is a horizontally scalable process, or just optimizing your deep learning models and GPUs. So diving a little bit deeper into these thallenges, the first one for the open source, I'm just showing you the reference of the diagram here. You have some upstream package providers, and you will mirror them into an internal repositories. This could be your Artifactory, your Conda teams, Anaconda teams, and you might have like whitelists in there. Then you have like policies and governance aspects of it that is dictating how you are building your packages and data science environments. And then you're providing those specs into a CI/CD or an automation task runner that is building these environments continuously and making them available for downstream users. The second challenge was the enterprise integration, and Jupyter Hub has been built in a very modular manner, and it has a lot of ways to extend. In fact, UV Panda wrote a blog post last year where he listed 99 ways to extend this ecosystem. So that's a good news for us. Is good news for enterprises. You can have many different types of spawners. We're working on a GPU spawner for private machines. Now, the third is the new scale. And one of the important part of this is that, as you are going from like small data to like large data and like just scaling out to like heterogeneous infrastructure, you want to minimize your technical cost of migration. And I'm just showing a code example on the local, this is your sort of the local Python code. And then you can make it distributed by using like Dask bag. And like this could now be scaled out. Up next in our demo, Ben and Nathan will walk us through this example, and they'll also just show us how we integrated a distributed logging mechanism for machine learning experimentation. With that, I will pass that over to Ben, and Ben, please take it away. Thank you.
Okay, so let's get started. You can see here that we do have a GPU available on the device. Now, this next part, there's a project that we created to extend Jupyter Hub with an experiment tracking system. This basically gives you distributed logging so that whatever containers, pieces of your training are running on, you can log actual objects, not just text, but binary objects into a central place so that you can reproduce your experiments. You can track absolutely everything involved with a particular experiment. And I'm going to be showing some of how that works. And we are open sourcing this project. It's called VE2, Verify Experiment Twice, and I usually refer to it as VV. So first I'm going to set up VV, and it gives me back this run ID. So this training I'm doing in this notebook is what we call a run. Now I'm going to get a list of all of these PCAP files. We put them up in Azure Blob Storage, and 4,400 of them. Some of them are pretty large. Reading and labeling, and basically building a set of files that we're going to process. We're not going to process all of them today, just 500, but that's 57 gig of data. Now I'm going to log that list of files to VV. This next part, I'm going to connect to Dask. We have Dask Gateway letting us connect, letting us spin up ad hoc a compute cluster from a Kubernetes cluster that's been set up in Azure. And this is just in an experimental mode, so it's not SSL protected. So forgive us for that. But I am going to put in the password and connect to the gateway. I guess I'm going to do that twice. Now, I can start to specify right in my notebook what kind of cluster I want. So I'm going to do 2 cores, 1 gig of RAM, and this particular container image, 0.7, that Hussain set up for me. I only need 1 gig of RAM, even though the files we're processing are often larger than a gig, because I'm streaming in each task, streaming the file through the steps of processing. Now let's make sure Nathan hasn't put a cluster up that's going to compete with me. He has not. And now I'm asking for 62 workers. So these are going to be the container I specified, 62 copies of it, running in Kubernetes with Dask on them so that I can spread my compute across them. And you can see them spinning up here. And Dask gives me a nice console dashboard where I can see my cluster. We'll come back to this. Now we connect. We upload our processing scripts. And we can kick off the job. And as Hussain showed an example of using a Dask bag, that's indeed what we're doing here. And I'm going to launch it now. Here we go. And now we can watch this happen in Dask. So a little bit about the task that's actually happening here. Each of these tasks is the processing of one of the PCAP files. And the way that we're processing it is to kick off one sub-process that streams the file down from Azure Blob Storage, un-gzipping it as it streams. That goes through a FIFO, a Unix FIFO, into a TCP dump process. And we're using TCP dump to just get the ASCII header information of all the packets of the file. Then the output of the TCP dump process goes into a third process, which uses some code we wrote to turn the stream of packet headers into a set of flows, flows being conversations over TCP. That set of flows is flow objects that we created, and those flow objects have code that lets them output as PNG images that we can look at, or as NumPy arrays that are the same as the images, but that we can put directly into our convolutional neural network. Also, the task that is happening, I'm logging to Vivi just to show that we can collect data from all these workers for the sake of reproducibility. I'm doing sampling in these subtasks. I'm not returning all the flows from a given file. I'm sampling them there within the subtask. And so I have logging into Vivi that gives a count of the flows and also how long it took. And this won't take too long to do. While it's running, let me just quickly show the code here. This TCP dump function is what's being handed to Dask to run a particular file. And it's then setting up the other processes, collecting the flows. It's telling Vivi what the run ID is. I passed that run ID in so that we have a single key for this entire run across all of the logging. And then it logs to Vivi an object. The object is a list containing the name of the file that was processed, the number of flows, and the time. The beautiful thing about Vivi is you can log any object you want. It's automatically going to serialize these, collect them in central storage, and then give them back to you, which we'll show later. Okay, we're almost done. We're just waiting for one of the larger files to complete here. You can see this one has been processing for a while, and that's that massive file. It's like 10 gig.
Just to point out just something that is going on is the script that Ben just showed earlier, we're just streaming the PCAP files. And like, this is why we don't need a lot of RAM in our workers. So like, that's a cool optimization of like you're using Dask to like actually stream the files instead of loading them all at once.
And that does involve some magic. Don't hate me, but I did write out a Python script from my Python script and then execute it. Okay, so we processed 500 PCAP files. Took 3 minutes and 46 seconds to go through that 60 gig. That would have taken a really long time if we didn't have Dask in our compute cluster. So now let's see what we've got. Okay, we have collected 50,000 benign flows. They were not classified as attacks. 5 infiltration, 10,000 FTP brute force, etc. And we can look at some of these. I'm not going to get into the visualization style, but you can reach out to us if you're interested in how we did this. These are some of the flows and what they look like in the visualization. I've now sampled again, downsampled, but done it in a balanced way. And now here's some random examples of some of the flows. High orbit ion cannon. Okay, so now we do all the NumPy stuff and build a proper set of tensors that we'll be able to pass in to our CNN. And these are the classes. The CNN has a multi-class output. And so we've got this list of classes here, which we'll get to later. So now we define the architecture. Standard. We didn't do anything fancy. This is straight out of examples. So let's go ahead and fit this model. And actually, tell you what, I'm going to change this to 2 epochs, because the ones we've been doing have all been 1 epoch, and I want to see if the accuracy is better. And that's going to give us a good use case for the VV logging, which you'll see in a bit. So we'll run this through 2 epochs.
And Ben, is this also running on GPU?
Yes, it is. This would be way slower if it wasn't, and we'd be sitting here for 6-7 minutes watching the little arrow. So you can see accuracy going up pretty nicely. And we should go into the 2nd epoch here pretty soon. All right, so 92% training accuracy on the 1st epoch. 98% validation accuracy, and that's on a 20% holdout set. Looks like Epoch 2 is going to get over 99% training accuracy. Yep. Seems to be topping out. Okay, so we're over 99% validation accuracy. So let's see what we've got here. We'll take a look at a confusion matrix. And not too bad down the center, although you can see we've got 1 class. I believe that's the infiltrations where there were only 5 examples. This one's not doing well. With 5 examples, it's not likely, A, that there's enough to train, and B, that there's enough in the validation set to even test it. So in production, we would throw out that class and not attempt to detect those. I'm now going to log my validation accuracy and the confusion matrix itself, just the object, to VV. And you can see how easy we've made this. Now I'm going to save the model and the text file describing the classes. Now I'm going to shut down my cluster. And with that, I will turn it over to Nathan to show us what we can do with what we logged to VV.
All right, so I'm going to show you guys our Voila notebook dashboards demonstrating VE2 in 2 distinct use cases. And let me go into what VE2 and Voila are for a second. So VE2 is a distributed logging system for experiment tracking that is integrated with Jupyter Hub, whereas Voila is basically an extension to Jupyter that allows you to cleanly display the results of your notebook for use in demos or interactive standalone apps. So the first dashboard we're looking at will be pulling back the events from a specific run logged by VE2. And Ben sent me this specific run ID. So we just have to input it into the field and fetch our run. And this will return to us a pandas data frame containing all the events and logs that happened during the specific run. I'm going to move on to our second dashboard, which shows us how we can compare the results of different runs over a period of time with confusion matrices. Let me switch over to this. And Ben, I'll let you talk on this one.
Okay, first, we're showing just an example of pulling the project log from Vivi. When you call vivi.setup to get a run ID and log to it, you pass a model ID and a project ID. Easy way to associate models into a project. And then you can fetch a log of everything that happened for a given project. Comes back to you as a pandas data frame. And we can see there's a lot of information logged. This is because we're logging every worker task. You can log strings, floats, or binary objects. So now let's scroll down and look at a couple of these confusion matrices that were generated by the runs. You can see that they are different. There's a lot of random sampling in these runs, even out at the tasks. We don't process the same set of files each time. We don't pull the same flows from each file each time. So it's very useful to log something like these confusion matrices so you can compare across runs and see if you're getting the same general performance out of your model each time. And indeed, while the numbers here are different, especially if you look at things that were misclassified as benign, you see roughly the same order of magnitude of misclassification, but they occur in different places. You can see that the infiltration class, as we suspected, in multiple runs is useless and should be thrown out. But you can see that the other classes, and would you scroll up a little, Nathan? Yeah, that the other classes we're getting very good results on even across runs. Just a small example of how you can use Vivi to monitor progress across all the many runs you do when you're trying to get a model to work properly. This is all about getting toward reproducibility. So when you do get it to work right, and then you change some stuff and it doesn't work anymore, you can just go back to what you had before. Vivi, in the enterprise version, will log the actual code from the notebook. It will log the user that ran the code, all kinds of telemetry about that run. And I will turn it back to Hussain.
Awesome. Thank you again. So as you guys just saw, that we've just showed you guys 3 examples of how we could extend a machine learning platform based on the hub. The first one is just Dask, where we use Dask and Dask Gateway to just scale out our machine learning workflows. The just second one was we extended our Jupyter Hub with Javala dashboard and extensions. And then we also added a custom experiment tracking enterprise just service that was integrated with the hub.